Okay, starting chapter 5 of Statistical Rethinking, second edition. We'll go through questions 1 and 2 of the easy questions, and there's no coding here in the first section, the easy section of the questions. So, okay. So this chapter starts. So this chapter deals with multiple linear regression. In the previous chapter, we were dealing with simple one variable linear regression, which might look something like this, right? Where we have a single explanatory variable, x, trying to explain our outcome here, mu, okay? And so multiple linear regression, of course, is just when we have more than one explanatory variable, okay? So question 1 asks us to identify which of these equations qualifies as a multiple linear regression, okay? So in order to be multiple linear regression, first we need to have an outcome variable that is being regressed on predictor variables, and they all fulfill that, right? They're all mu being regressed on some variables, okay? And then the next thing that to be multiple linear regression is that we need more than one, predictor variable. But not just a predictor variable, we need more than one, well, we need the predictor variable to be multiplied by its coefficient. So we need our variable and coefficient pairs, okay? And so the ones that fulfill that are 2, right? So we have x and z, and they're being multiplied by their coefficients, okay? And again, the coefficients are what we will try to solve for once we have all of the data. We notice that that number 1 is not a multiple linear regression, because even though there is 2 terms here, the alpha is just a parameter. There's no explanatory variable associated with alpha, okay? And now similarly for 3, well, not similarly, a different scenario. Here we do have 2 explanatory variables, x and z, okay? But they're both of them are just being multiplied by a single coefficient. And so the reason that this doesn't qualify as multiple linear regression is because this variable right here, or x minus z, we could just call that a different variable. We could just call that w, and I've kind of explained that down here. But we could just call x minus z w, in which case 3 becomes just univariate again, right? So that's 5E1. And let's go to 5E2 just because we have time. So in this question, we are asked to write down a multiple regression that is evaluating the following claim. Animal diversity is linearly related to latitude, but only after controlling for plant diversity. So we're going to write down the linear model for this. It's asking us to ignore priors, so we won't establish any priors for this. So let's start trying to write this, okay? So first we need an outcome, all right? And so we're going to use A for animal diversity. And so I'm going to think of this as the number of species in a given area of land. That's what I'm calling animal diversity. Okay? And we're asked to, so all that we know about at this point in the book is normal linear regression, okay? And so that means that we're going to assume that A, animal diversity, is normally distributed with a mean mu and standard deviation sigma. Okay. And now we need to regress our outcome, animal diversity A, on latitude, right? That it's linearly related to latitude, okay, while also controlling for plant diversity, okay, after controlling for plant diversity. So, so what that will look like is this right here, right? So we have our explanatory variables L and P and their coefficients, beta L, beta P, okay? Now, notice that this formulation right here, and this is just the case with regression, that this would also help us to evaluate a different claim up here. So instead of saying animal diversity is linearly related to latitude, but only after controlling for plant diversity, we could actually flip that, right? We could actually say animal diversity is linearly related to plant diversity, but only after controlling for latitude. And it would be this same thing here. So in other words, as terms go into the linear regression, each term is acting as a control. So what you get out at the end is, or what you're trying to estimate at the end, or what you get out at the end, is an estimate for the effect of an explanatory variable, L or P, after controlling for all other explanatory variables in the model, P or L. Okay, so I hope that made sense. Okay. Now, finally, the question does not ask us to consider an interaction, and so an interaction between L and P. For instance, perhaps animal diversity is affected differently by L, by latitude, at different values of P, of plant diversity, right? So for instance, maybe generally as you go up in latitude, there is less animal diversity, but if for other circumstances there is greater plant diversity, maybe the effect of latitude is diminished, okay? And that would be an interaction term, and we might write that term like this, beta LP, and then we multiply the two variables, L and P. Okay, and that would be an interaction term. Again, the question doesn't ask us to do that, so I don't know that you need to do that, but I am just doing it here for fun, I guess. So when we, so one more thing that we want to consider is an intercept term, okay? And an intercept, alpha, this value, we can think of the value of alpha as being the alpha, or the value of animal diversity when both latitude and plant diversity are 0. So this would be at the equator at an area where there are no plants. And alpha then would be the animal diversity in that circumstance, okay? So when we put it all together, our model might look like this, right? So animal diversity is normally distributed with a mean mu, standard deviation sigma, and mu is being regressed on an intercept, as well as our two explanatory variables, and I have put in an interaction, although that may not be necessary. So in order to make this a fully Bayesian model, we would just need to add priors, but we're not doing that here. And then the last thing that I want to point out, and maybe whet appetites for future content of the book, and I guess these videos as well, is that there may be an assumption hidden in here, or not so hidden, made very obvious in here, which is why we want to use this type of notation. It makes our assumptions very, very obvious. But there's an assumption embedded here that may be inappropriate. Okay? And that assumption is that animal diversity is normally distributed. Okay? Or said more correctly, that after I control for latitude and plant diversity, that what is left over, called the residuals of animal diversity, are normally distributed, right? And the reason that this seems possibly incorrect is because a normal distribution that I have here, so let's say that I count for latitude and what's P? Plant diversity. Well then, what is left over for animal diversity, that's the residual, a normal distribution assumes that the thing that is left over could be negative, right? So in other words, there could be less than 0 animals in some area. And this doesn't make sense. We can't have negative animals, okay? And so we could correct that, possibly by regressing the log of animal diversity, but there's a preferable technique where we don't assume a normal distribution for A in this case. We assume some non-normal distribution that just does not allow negative values. But that is a topic for later chapters, but it's a topic of generalized linear models, and so that will be coming up later on in the book. Okay, thanks.